So what we're going to look at today is we're going to be looking at something called the Gram Schmidt process. And so the idea here is that we're going to imagine we have a basis. Now this basis is made up of a certain number of vectors, say n different vectors. And so what we'll do is we'll think that that basis is going to do what we call generate the space. That is that we can create anything within the space using a linear combination of however many vectors are inside of that set. So there's like n different vectors. Now here's the thing about this though. The problem with this is that they may not be really very easy to use, these basis vectors. And as we've seen as trying to do like change of basis work and that sort of thing, that sometimes basis vectors, while they actually allow us to generate the space, they don't know how to do it efficiently, or they don't do it in a really clean way. Now, what we learned about in our immediate previous lesson was these things called orthonormal bases. And an orthonormal basis is where the vectors in the basis, right, are all orthogonal, and they are also all unit length. So they're orthogonal and unit length. Now, if you think about this, it's really very, very handy, because what ends up happening is if they're all orthogonal, you can kind of imagine having a coordinate system in which, you know, you go a certain direction here in this direction, certain direction here in this direction. We know that they're going to be at right angles, much like the standard basis. And since they're orthonormal, all we've got to do is we've just got to basically multiply, whatever the scalar is that we multiply by that basis vector, we know it's going to move, or it's going to move our resulting vector in that direction, exactly that magnitude, right? Because the vector is normal, and so since it's normal, that means that whatever scalar we multiply by, that ends up being the magnitude of that particular vector. So we can actually, in fact, figure out the magnitude of the resulting vector simply by just adding up the values and adding up the components of the vector that we're actually trying to generate. Okay, so it actually ends up being really, really handy. And if you think about it from a visualization standpoint, it makes a lot of sense, right? Our normal way of visualizing coordinate systems, which is basically what a basis is to think about like the x, y, and z axis. They're all orthogonal. They're standard basis vectors. They're all unit length, okay? And so that actually makes it really easy for us to think about like rectangular coordinate systems, things like that. So what we're going to do in the Gram Schmidt process is we're going to take a basis and we're going to transform that basis into an orthonormal basis. So basically we're going to take the vectors that are in the basis and we're going to transform them into a different basis that actually spans the same space. So it'll be a basis for the same space, but the vectors will now be orthogonal and they will also be unit length. All right, let's talk about the process for the Gram Schmidt process, okay? So what we're going to do now is we're going to imagine we have a vector space V, and V is going to equal the span, and we have a basis for V made up of x1, x2, x3, so on and so on and so forth, okay? So this actually ends up being the basis that we're looking at, okay? And what we want to do is we're going to generate an orthogonal basis. And the orthogonal basis, we're going to start out with the first vector that we're going to have is going to be x1. Okay, it's the vector x1, and actually x1 is going to equal v1. So there's the first element inside of our orthogonal basis is just going to be v1. We're going to put that first vector going to be put into there. Now I'm going to take my next vector, and that's going to be x2. Okay, here's x2. Let's imagine that's x2, and notice it's not actually orthogonal to our vector. All right, and so what we're going to do is we're going to generate an orthogonal projection. Okay, so I'm going to basically create, okay, or I'm going to, in fact, create an orthogonal projection of v1 onto x1, or onto x2, excuse me. I'm going to take v1 onto x2. So this thing here, this length here is p of w, or not w, but p of x2 Next up, what I'm going to do is I'm going to draw x2. So here's x2, okay? And what I'm going to do with x2 is I'm actually going to create an orthogonal projection onto V1. Okay, so I'm going to create a projection, orthogonal projection. This is the projection of x2 onto V1. And it's that projection. And so remember that projection, P of x2 comma V1, is going to end up equaling x2 with the inner product with V1 divided by the magnitude of V1 squared and then times V1. So remember that that's actually going to be that particular vector, right? So we're going to create that, and now the orthogonal vector that we're going to be looking for is this one right here. Okay, that one's actually orthogonal. Okay, it's orthogonal to V1. Okay, and that's going to be called V2. And what that is that's basically x2 minus P of x2 V1. So my V2, my second vector, V2, is going to now equal V1, not V1, but x2 minus x2 comma V1 divided by the magnitude of V1 squared times V1. And that now is a vector that is orthogonal to that is orthogonal to V1, okay? And in fact generates the same plane as x1 and x2, okay? Right? It's now just orthogonal. So what it's done is it's changed x2 to an orthogonal vector, and the span of V1 comma V2 is actually equal to the span of x1 and x2. All right? So basically, we were going to generate the same exact space now. It's just that what we've done is we've now made the two vectors orthogonal. So now I've got V1 and V2. Those are my two vectors. Now I need to go figure out how to make V3. So this basic idea is going to be what we use in order for it to have the entire Gram Schmidt process. Let's talk about finding now our V3, our vector V3. So V3, okay, what we're going to do is we're going to start out with x3. It's got to be we got to have a particular place to start with x3. And then what we're going to do, right, is we're going to subtract out the orthogonal projection P of x3 onto V1. All right? And so what will happen there is we know that this gives me an orthogonal, this is orthogonal to V1. All right, that's the first piece. And then I'm going to subtract out the orthogonal projection P of x3 onto V2. And doing that x3 with the P of V3 at V2, that makes it orthogonal to V2. Okay, so basically what we've done now is we've kind of subtracted off the non-orthogonal parts of x3, the ones that are kind of like redundant inside of V1 and V2. And what we're left with then is we're left with this vector V3, okay, that gives us the same information, but now is orthogonal to, so it's orthogonal to V1 and V2. Okay, and if I rewrite that, I'm going to get V3 is thus going to equal the inner product x3 with, or excuse me, x3, the vector x3, minus the inner product x3 comma V1 over the magnitude of V1 squared times V1 minus x3 inner product with V2 divided by the magnitude of V2 squared times V2. Okay? And that now is going to give me V3. So now I'm like, oh, okay, great, I've got V3. Now, it's called a process because this is what we're going to be doing. By the way, one of the things that you can kind of see here, you might want to see here, is you can see that, in fact, this piece here, right, is going to end up giving me a linearly independent vector, all right, to V1 and V3, all right? And that is because we're assuming that x3 was a basis vector beforehand, all right? And all I'm doing now is I'm subtracting out some scalar multiple of v1 and v2, right? So I should be left with like basically the linearly independent part of x3. That's kind of the idea that you're dealing with here. You're not actually making you're not going to do anything to the vector to make it now linear, to make the set now linearly dependent, okay? That's kind of how that works. So if we think about v4, v4 is now simply going to be equal to, we'll have x4, and then because that's the process, it's going to be minus x4 inner product with v1 divided by the magnitude of v1 squared times v1 minus x4 v2 divided by the magnitude of v2 squared times v2 minus x4, this is magnitude of v2, or excuse me, v3, over the magnitude of v3 squared times v3. All right, that's v4. We keep doing this, so on and so on and so forth, right, until we get to vn. So vn is going to start out with xn, the last vector in our basis, minus the orthogonal projection of x4, or excuse me, xn onto v1 minus the orthogonal projection of xn onto v2, so on and so on and so forth, ad infinitum, okay? And that is the Gram Schmidt process. And our set, v1, v2, v3, all the way up through vn, is going to be our orthogonal basis. So let's take a look at this example. We'll start out with, we're going to have x1. We want to find an orthogonal basis for v equals x1, x2, x3, or it's actually the span of those. And we'll have x1 is 1, 0, 1, 0. x2 is 1, 1, 1, 1. x3 is negative 1, 2, 0, 1. So I've got three vectors. So what I'm going to need to do is I'm going to need to find three orthogonal vectors. So I'm just going to write down what their equations are going to be using the Gram Schmidt process. So x1 is going to equal v1, or actually, excuse me, other way around. We're going to write v1 equals x1. So we already know, hey, already there, 1, 0, 1, 0, that's in our orthogonal basis. v2 is going to equal x2 minus, and it'll be the orthogonal projection, so that's going to be x2 inner product with v1 divided by the magnitude of v1 squared times v1. And then v3 is going to equal x3 minus x3 inner product with v1 divided by the magnitude of v1 squared, v1 minus x3 inner product v2 divided by the magnitude of v2 squared times v2. And so those are the equations for our inner products. Or excuse me, those are the equations for our orthogonal vectors. Now our job is to just go in and do them. Okay? So I'm going to start out. I know my first vector, v1 equals 1, 0, 1, 0. v2 then is going to equal 1, 1, 1, 1 minus, and what I'm going to do a little bit of scratch work on this side because I just find that it's easier. So I'm going to take, I've got 1, 1, 1, 1 dotted with 1, 0, 1, 0. Okay, so that's going to be my inner product. Okay, and so that equals 1 plus 0 plus 1 plus 0, so that equals 2. And then the magnitude of v1 is going to equal the square root of 1 squared plus 0 squared plus 1 squared plus 0 squared. So that equals just the square root of 2. So what I'm left with is that this is going to then be 2 over the square root of 2 squared, right? So that's going to end up being 1 times 1, 1, 1, 1, or excuse me, minus 1, 0, 1, 0. So we're going to take v1, right? Okay. So we took the magnitude of v1 squared. We took the inner product of x2 with v1. Okay. And now we're going to do the subtraction. Notice that this is equal to 1. So we get 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. And so now that is our second orthogonal vector, and that's v2. v3 now is going to equal, it'll be, we're going to first take, we're going to have x3. So x3 is negative 1, 2, 0, 1. All right, so now what we need to do is we're now going to take v3 times negative 1, 2, 0, 1. All right, and we're going to subtract. And so first I need to find the dot product of x3 with v1. So if I look here, I've got x3, negative 1, 2, 0, 1. And then my v1 is dotted with 1, 0, 1, 0. This equals negative 1 plus 0 plus 0 plus 0, which equals negative 1. And we already know that the magnitude of v1 squared is just equal to 2. So this is going to be minus 1/2 times 1, 0, 1, 0. Now I need to subtract. I need x3 dotted with v2. So x3 again is going to be negative 1, 2, 0, 1. Dotted with v2. So note that that's going to be 0, 1, 0, 1. Dotted with 0, 1, 0, 1. And that'll end up being 0 plus 2 plus 0 plus 1. And that ends up equaling 3. And then we'll take the magnitude of v2 squared. So the magnitude of v2 squared is just simply going to be 0 squared plus 1 squared plus 0 squared plus 1 squared, which just equals 2. So this gives me 3/2, and we're going to multiply that now by 0, 1, 0, 1. I made a notational mistake. This actually should be negative 1/2, right? Because this is a negative, so negative 1 over 2. Just to note that, that should be changed. So now this is going to be, what we're going to do, I'll do the first subtraction. So this is going to be negative 1 plus 1/2. So this is going to be negative 1/2, comma, and then this will be 2 minus 0, so that's, or 2 plus 0. It's 2. And then 0 plus 1/2, so that'd be 1/2. And then 1 plus 0, and that should be 1. Then we'll subtract from that 3/2 times 0, 1, 0, 1. And so this ends up giving me negative 2, or excuse me, this is going to then be negative 1/2, because that's negative 1/2 minus 3/2 times 0. 2 minus 3/2, so that ends up giving me 1/2. 1/2 minus 3/2, so this is just going to be 1/2 again. And then 1 minus 3/2, and so that ends up being negative 1/2. So my orthogonal basis now is going to be, my vector space V can be written as the span of 1, 0, 1, 0, comma, 1, 1, 1, 1, comma, negative 1/2, 1/2, 1/2, negative 1/2. All right, and if we go through and we take the dot product of each one of them, we do them pairwise, what we should get is we should get 0 for each one. So let's check. We get 1, 0, 1, 0, dotted with 1, 1, it's actually, right, it's 0, 1, 0, 1, 0, 1, 0, 1. We get 0 plus 0 plus 0 plus 0. Great. Take 1, 0, 1, 0, and we'll dot that with negative 1/2, 1/2, 1/2, negative 1/2. What you get there is you get negative 1/2 plus 1/2. That equals 0 again. And I'll let you do the other two for yourself. Okay. So Gram Schmidt process. All right. Basically, what we're going to be doing is we're going to start out with, take the first vector. That's going to be the first part of your orthogonal basis. Then we're going to subtract out the orthogonal projection of your second vector with your first constructed orthogonal vector. So the notation really is going to matter. Notice, and I did this actually a couple times as I was going through here, so be very careful about this. Notice that what you're going to do to find V2, right, okay, is you're going to be dotting with V1. Not necessarily X1, although they are the same thing, but you're going to be dotting with V1. This becomes especially important when we get down to like V3, where now we're dotting with V2. So you created V2. V2 is not one of your original basis vectors. Okay? So you need to make sure that your V2 goes right into there, right? Okay? This V2, that becomes the new V2 that's listed here. And for V3 and V4, so on and so on and so forth. And the process, right, is just for each additional vector, okay, you're going to subtract out the orthogonal projection of every other now orthogonal basis vector, right? And that's the Gram Schmidt process.